Okay, let us discuss the next concept, that is relation between sequence component of phase and line voltages in star connected system. So first we are discussing for star, then we'll go for the delta. So we know that VL is equal to root 3 times the V phase, that is line voltage is equal to root 3 times of the V phase voltage. Consider A, B and the C are the phase voltages, and having the sequence of A, B and C. Okay, so this is the figure which we are considering, that this is a point A, B and the C. This is star connected system where the phase voltage is VA and this is phase voltage VB and it is VC. Then the line voltage between the phase A and the B is VAB. Similarly, for the phase B and the C is VBC. Similarly, for C and A, it is VCA. Then this is denoted as between A and B is VC, and between B and C it is VA, and between C and A it is VB. So how do you say that? This is opposite to that of the vertices. Okay, between AB it is opposite to the vertices C. Okay, C. Similarly, between VBC it is opposite to the vertices is A. Similarly, for CA it is B. Then from this what we can see is the three line voltage of the system is VAB, VBC and VCA. Then from this, by using this, we can write it as VBC is nothing but VBC, VC minus VB. Then VCA can be written as VA this minus this. Similarly, for VAB it is VB minus VA. Or else we can take it in another sign, that opposite of that sign. So in place of this is going to be minus and this minus is going to plus. You can use whatever the things you feel that free, you can use it. So similarly, that opposite to the vertices BC is VA, between CA and is VB and AB is VC. Okay, so that is part. Then we understood that what is the relation between the phase and the line voltages. We have to calculate that the positive sequence component of the line voltage, similarly for the negative sequence and for the zero sequence. So here we are writing that positive sequence component of the line voltage. Do not get confused here. We know the equation, that is VA1 is equal to 1 by 3 times of VA plus A into VB plus A square into VC. Then VA, we know that VA can be written as, here it is VB minus, VA can be written as VBC. What is VBC? VBC is nothing but VC minus VB. Okay, so this term. Then A into A is similar, VB can be written as VA minus VC. VA minus VC. Similarly, for the A square is same, VC can be written as, it is VB minus VA. Just we are substituting this. Then do a simplification, that the term, okay, here we have taken A, so this is the A into VA, this term is over. Okay, this is what. The next we need to find that it is a VB. Where is a VB? So here this is A square into VB. Already we have A and we will multiply this A, so the resultant will become A into VB. So next term is VC, here it is a VC. Then already A is there, if I am multiplying that A square, so that will become A cube. So A cube is nothing but 1. Okay, this term. The next term is, so here this term, it is multiplied by minus A square VB. Sorry, it is minus A square VA. take down minus a square is the outside, so inside of the bracket I'll consider it VA. And for the VB, look at this, here it is a VB, so already there is an a square, so if I multiply it by a, then only I will get a cube. A cube is nothing but 1, so a into VB. Similarly for the VC here, okay, this is nothing but a into VC, okay, a into VC, already there is a square, so if I am multiplying by a square, then I will get a square into VC, so that is nothing but a into VC. So what is a common term here? This is a minus a square is a common, okay, so the matrix will be, sorry, the equation will be of a plus ba plus a into VB plus a square into VC. Then but the thing is, we know that a into VA plus a into VB plus a square into VC is equal to, it is a 3 times of VA. So this you need to remember that we are going to prove this, okay, in the later part of the chapter, okay. If it is containing only the positive sequence, this should be 3 times of the VA. Similarly for the negative, and there is no value for the 0, okay. So we know that a square, sorry, a into a square, so a minus a square, that can be written as, that is equal to j root 3. So substitute these values, so in this equation, okay, at this point, so we know that a minus a square can be written as j root 3, and similarly for a plus a into VB plus a square into VC can be written as 3 into VA1. So that is nothing but, that is equal to VA1 is equal to, it is j root 3 into VA1. Okay, this is the line, this is the phase. So what does this? So hence what will happen? Positive sequence component of the line voltage, it is root 3 times of the positive sequence component of the phase voltage, and which is going to lead the corresponding phase voltage by 90 degree. It means that it is advanced by at an angle of 90 degree with respect to the phase voltage. That is the meaning. Okay, similarly for the negative sequence component of the voltages can be written as, so this is VA can be written as 1 by 3 times of VA plus a square into VB plus a into VC. So substitute that VA value is VC minus VB. It is not a plus, this is minus, okay, this is minus, okay, VB is nothing but VA minus VC. So similarly, what is the VC value? VC value is VB minus VA. It's not CA, it is VA, okay. Then so by simplification, consider that a square into VA, this term. So if we take it that the a square is common, so a we need to multiply it by VA. Similarly for a into VB, so if already there is a square, so if I multiply by a square, then only I will get a to the power of 4. So this can be written as a3 into a to the power of 3 into a, that is a to the power of 3 is nothing but, or the a cube is nothing but 1. So this is nothing but a, okay. Then for the VC, okay, just it is 1 into VC. So already a square, if I make it that multiplied by a, we'll get V a into VC, okay. So next term is minus VA, okay, for this already minus a into VA, okay, minus a, already there is an, if I multiplied by VA, we will get. Then next term is a square VB. So there is already a, consider this part, okay. So already minus a is there, if I multiply by a square, then we'll get a, okay. Then last term is VC, okay, already this is a square into VC, okay. So already a, so if I'm making multiplied by a, we'll get a square into VC, okay. So here consider that a square minus a is a common, and multiplied by the equation, that is a VA plus a square into VB plus a into VC. Okay, so because VA plus a square VB plus a into VC, so this is equal to, it is 3 times of VA2. Okay, that is the meaning that, so if the network is consisting only of the balanced negative phase sequence component, it is, so it is a 3 times of that value. Okay, that we are going to address you later part of this chapter. Okay, so we know that a square minus a can be written as minus j root 3. Substitute that, we will get VA2 is equal to minus j root 3 times of VA2. So this is nothing but negative sequence component of the phase voltage, which is going to lag the corresponding phase voltage by 90 degree. So here positive sequence is advanced, it is lagging by 90 degree for the negative sequence component. So similarly for the zero sequence component, we know that it is VA0 is equal to 1 by 3 times of VA plus VB plus VC. So substitute these values, okay, we'll get the 0. So there is no uh, zero sequence component of the line voltage in the case of 0. Okay, let us solve some simple numerical on this topic. Consider positive and negative sequence component of the phase voltage of a three-phase system are VA1 is equal to 230 at an angle of 30 degree, and VA2 is 60 at an angle of 60 degree. Determine the positive and negative sequence component of the line voltage. Let's solve this. Consider that positive sequence of the line voltage. So we know that we already derived VA1, that is capital VA1 is equal to J root 3 times of VA1. This is the line, this is the phase. Substitute that VA1, it is 230 at an angle of 30 degree. So we'll get 398.37 at an angle of 120 degree. Okay, volts. Similarly for the negative sequence of the line voltage, we have done that. VA2 is nothing but it is minus j root 3 times of VA2. Okay, substitute that VA2, it is 60 at an angle of 60 degree. So we will get 103.92. So similarly for the zero sequence of the line voltage, it is not given, it is 0. Okay, so now we have to calculate the line voltage of the system. So that is nothing but VA is equal to VA0 plus VA1 plus VA2. Okay, similarly for VB is equal to VA0 plus A square into VA1 plus A into VA2. So similarly for the VC is equal to VA0 plus A into VA1 plus A square into VA2. By substituting that VA0, VA1 and the VA2, you will get VA is equal to 312.71 at an angle of 110.43. For the VB, we will get 411.7 at an angle of 14.62. Then for the VC, we will get 491.13 at an angle of minus 126 degree. Let us discuss the relation between sequence component of the phase and line voltages in delta connected system. So consider that we know it is delta connected system. This is a node is A, this is B, and it is okay, the node is B, okay, and it is C. So here consider that a delta connected system is a three-phase system. These are the line currents IA, IB, and the IC, which are entering into the delta connected system. So we need to calculate what is the phase current. So that is here IA between the phase A and the B is IAB, and between the B and the C it is BC, and between the C and A is nothing but ICA. So these are the phase current which is flowing in the delta connected system. So consider that IA here can be written as, so this IC, okay, this IC here, it is entering at this point IC, okay, and it is IB which is going out. This is entering and this is going out, so can be written as, it is entering is a plus and going out of the network is considered as minus. Similarly for the B point here, okay, so what is that current at this point B? IA is entering, okay, IA is entering at this point, and IC is going out of the network, so this is minus. Similarly for the IC, the point, so B is entering, okay, this is a point B is entering, and IA is going out of the network, okay, so this point, so this is IB minus IA. Or you can consider which one is entering, you can consider as a negative, and going out of the network you can consider as a positive, okay. So now apply that the KCL at the system. So we know that IA can be written as IC minus IB. So similarly IB can be written as IA minus IC, and IC can be written as IB minus IA. So we have to calculate the sequence component of the line current. Already we know that IA1 here, do not get confused here, it is small IA1, this is nothing but the line, okay, is equal to 1 by 3 times IA plus A into IB plus A square into IC. So substitute these values. What is IA? IA is nothing but IC minus IB here, okay. Similarly for IB is nothing but IA minus IC, and for the IC it is IB minus IA. Okay, do a simplification that consider A is a common term, okay, A into IA, and we need to consider the B part, okay, plus this is A square into IB, so already there is A, so if you multiply it by A, so this will become A square. So here it is IC, it is 1 into IC, A, if I multiply it by A square, that's A cube, so A cube is nothing but 1. And for the next we have to consider it is A square minus IA, okay, so this is multiplied by A square IA minus, okay, minus A square IA will get. And for the B, consider that, okay, here it is minus IB, already there is minus A square, if I multiply it by A, IB will get A cube. And for the IC, it is A into IC, okay, minus A square already is there, so if I multiply by A square, so it is power 4, so there is nothing but A. So do a simplification that, so common term is A minus A square, so we'll get multiplied with IA plus A into IB plus A square into IC, okay. Consider that A into IA plus, sorry, IA plus A into IB plus A square into IC can be written as, it is a 3 times of IA1. So we know that it is A minus A square, it is minus J root 3. So hence we will get the final one, it is minus J root 3 times of IA1, okay. Similarly for the negative sequence component of the line, okay, so this is nothing but IA2 can be written as 1 by 3 times of IA plus A square IB plus A into IC. So substitute this IA plus IB and the IC, do a simplification. So consider that A square IA is common, okay, A square is a common, so multiplied by IA. Similarly for the IB, okay, here it is A into IB, already there is a square, okay, so yes, okay, consider that, so this is done, A into A square into IA, so not this, okay, So here, so similarly multiplied by A into IB plus A square and IC, and writing that, doing the simplification, the final we will get 1 by 3 times of A square minus A multiplied by IA plus A into IB plus A square into IC. The final equation you will get 1 by 3 times of minus J root 3 into 3 into IA2. Why? Because IA plus A into IB plus A square and IC can be written as it is 3 times of IA2. The finally you will get it is minus J root 3 times of IA2. So similarly for the IA0 can be written as it is IA plus IB IC multiplied by 1 by 3, we will get the final 0. So it is the meaning that what we can understand from this, that so whereas in case of the line current in the delta system, it is okay in the delta connect system, it is root 3 times of the phase voltages, and the positive sequence of the line current, which is going to lead respective to the phase current by an angle of 90 degree because of the zeta. And similarly for the negative, it is going to lag with an angle of 90 degree. Finally, zero component is 0. So it doesn't mean that, so whereas in case of the delta connected system, zero sequence component, the line current is not offset. Okay, so this will be made, it is in the clear that the zero sequence of the line current, it is IA is equal to 0. So it doesn't mean that the zero sequence of the phase current IA naught is means it is IA naught is also 0. Okay, so if it is 0, so it is meaning that the capital IA naught is also 0. Let us solve a simple numerical on delta connected system. Consider that a delta connected balanced resistive load which is connected across a unbalanced three-phase supply. Find the symmetrical component of the line current and the delta current. Let's solve this. Okay, the A, B and the C value. So we know that IA plus IB plus IC is equal to 0. Okay, so IC can be written as it is minus of IA plus IB. Why we are doing this? Because we don't know what is the value of the current IC. So we have to calculate that. Substitute that IA and the IB value. Okay, IA and the IB value will get 18 at an angle of 154 degree amperes of the current. So consider the symmetrical component of the line current. So that is IA1 is equal to 1 by 3 times of IA plus A into IB plus A square into IC. Substitute this IA, IB and the IC value. So and also consider that A is nothing but plus 120 degree, A square is nothing but 240 degree of the angle. Okay, finally we will get 13.94 at an angle of 41.86 degree amperes of the current. So similarly for the IA2, so we will get 1 by 3 times of IA plus A square IB plus A into IC. So substitute these values of IA, IB and IC, and A square is 240 and A value is 120. So finally we will get a 4.65 at an angle of 111.57 degree amperes of the current. So finally IA naught is nothing but 0 because so we know that IA plus IB plus IC is equal to 0. No need to do a calculation. So we have to calculate the line current or entering in the delta connected system. So therefore we have to calculate the sequence component of the delta. So that is nothing but capital IA1 we have to calculate. So that is equal to IA1 divided by J root 3, means that it is IA1, small IA1 is equal to J root 3 times of capital IA1. So we have to calculate what is the capital IA1 is equal to IA1 small IA1 divided by J root 3. So finally we will get 8.05 at an angle of minus 48.14 amperes of the degree. So similarly for IA2, so this is nothing but IA2 small IA2 divided by minus J root 3. So substitute this, minus J is nothing but 90. So when it is going to numerator, this is going to become plus 90. Okay, 2.68 at an angle of minus 21.57 amperes of the current. So finally, I0 is 0 because small I0 is 0.